Welcome everyone to this new video. In this video we're going to learn about evapotranspiration, and to do that we're gonna solve three different problems. Let's get started with 4.1. How much water is needed in acre feet, so in volume, for 100 acres of corn growing at north latitude of 27.5 degrees during the month of May if precipitation is assumed at 0 and 150% of the water must be provided. The mean monthly temperature is 67 degrees Fahrenheit. So we are not gaining any water due to precipitation, and we have to provide 1.5 times of that water. To solve for this, given these values, we're going to use the Blaney and Criddle equation, which is a very useful equation to solve for evapotranspiration. This equation says that evapotranspiration equals to a K constant, which represents the consumptive use or evapotranspiration coefficient. Another way to think of this is like remember the class A pen, how it has a precipitation coefficient there, a C. This has a very similar meaning. It's to regulate how much water actually is being evapotranspirated. The P is the percent of daytime hours years, and we're gonna get it from table 4.6 down here. K, this coefficient, we're gonna get it from this table. The T mean is the mean monthly temperature in degrees Fahrenheit, and we get the evapotranspiration in inches using this equation. So solving for, so we have, let's do it over here. This K value, let's find, we're growing corn, so we go to the table, we see the crop and the K values. We have given all the other data, but for this problem we don't need to focus on that. So for corn, we got a range between 0.75 to 0.85. If you want to be conservative, you might want to use 0.85, so that would be 0.85, the value of K for this problem. The percent of daytime hours per year in the study month, we need to go to the table 4.6, and we're working in the month of May, so at 27.5 degrees north latitude. So that would be right between 25 and 30. So for May we have 8.61 and 8.72. No, that's April, sorry. 9.33, 9.53. So half of it is gonna be, the average of those two is gonna be 9.43. 9.43. Now the monthly temperature we are given, that is 67. And all we need to do now is just plug for the value. So if we do this down here, ET equal to K times P times T, the temperature, divided by 100, and we get 5.37, and we get this in inches. I think this must be an empirical equation, because I don't think the units are gonna match. So that's the evapotranspiration volume in inches, or depth. We are asked to solve for the volume given this area of acres. So to get the transpiration volume on this area, we're gonna have to multiply that by the area. However, I was forgetting, we need to provide 150% of the water. So whatever value we got here, let's multiply it by 150%, which is gonna be multiply 1.5. So it's gonna be about 8.06 inches, and to get the volume of that, we're gonna have to multiply that by the area, which is gonna be equals to this times the area, which is 100 acres, but this is inches, so let's divide it by 12 to get it in feet. and with that we should get acre feet, and it's 67.13 acre feet. And this is right here the final answer for this problem. Yep, and we are done with this. So let's move on to the next problem. In this program, we are using a new formula. Let me see if I can make this a little bigger. Okay, so it says using the empirical formula 4.6, I have it down here. This is the formula for evaporation with a water temperature of 60 degrees Fahrenheit and air temperature of 80 degrees Fahrenheit and a wind speed of 10 miles per hour. What is the daily pen evaporation? We're given that the relative humidity is 40%. And then we need to do part B, which is a comparison. Let's start from solving part A. So we are given, this is the equation. The evaporation equals the saturated vapor pressure minus the atmospheric vapor pressure to the n, and the book gives us already a value. So these n, m, and b are constant values that you can find in the book. I already put in here. And then u represents the wind speed. So we're given that the wind speed is 10 miles per hour. So I put it here. Now we'll need to solve. We need to find the values for the saturated vapor pressure and the atmospheric vapor pressure. So to do that, the saturated vapor pressure should be the pressure of the water, the pressure of the water in the atmosphere when the atmosphere is saturated, like the maximum amount of water that the atmosphere can hold before it precipitates. So to do that, we're gonna have to use what is the vapor pressures of water, and convert it from, we are given the temperatures and we need the inches, we need it in inches of mercury. So for the saturated vapor pressure, we're gonna use water temperature at 60 degrees Fahrenheit. So that will be 0.522 inches of mercury. And then we need the atmospheric vapor pressure, but this value is related to at the air temperature. So let's see, to solve for this value, we're gonna have to use this equation that we saw when we solved for humidity problems, which is the relative humidity equals the atmospheric pressure over the saturated. But in our case, we need the atmospheric pressure, and the saturated, we can find it. We're given that the air temperature is at 80 of at a air temperature of 80 degrees Fahrenheit. We're gonna have about 1.032 inches of mercury. So we just need to solve now for this, which is gonna be the relative humidity is 40%. That's equal to 0.4 times 1.032. So this is our value of the atmospheric vapor pressure. And let's see. Okay, the vapor pressure, let me double check it, that's correct. 4128. Yep. So now all we need to do is plug in the values to solve for this, and that's gonna be equals to this minus this elevated to the n, all of that multiplied by m plus B times U, but U needs to be converted to a daily because we have wind speed of 10 miles per hour and we're asked for the daily pen evaporation, so we need to multiply that times 24 hours to get it in a day, times 24, and that should give us our answer, which will be 0.19 inches per day. And the reason why it's inches per day is because we multiply these miles per hour times 24 because there are 24 hours in one day. So everything, a lot of it is gonna cancel out. Even though I think this is all, I see it's empirical, so actually the units won't match. So yeah, whatever value you get from here is gonna be inches per day. Just make sure you account for the wind speed. You need to account for, like, if it's 2 days, you need to multiply by 48 and so on. So that's part A of this problem. Remember that to solve for EA, you have to use this equation if you are given the relative humidity. E sub O, which is the saturated vapor pressure, you can just get it from the given temperature, you can just get it from the table. Now for part B, this is if this is considered the average daily evaporation, what region of the United States is this characteristic of? Use figure 4.3 as comparison. So I got figure 4.3 right here. So we got 0.19 inches per day. In this figure, we are given the values in centimeters annual. So we need to multiply, get this in centimeters per year. And to do that, we're gonna have to get this value. I have it here. Yep, so we need to multiply by 365 days. And then we need to get it in centimeters, we need to multiply by 2.54. And yep, and that's about what it will be, centimeters per year. And now we can compare to this table here. So 179, I would say, centimeters per year. I was looking at it previously and it looks a lot like it gets higher, the values get higher over here. So it will be about, I would say, Arizona. So the answer for part B should be an area in Arizona. Okay, that was 4.5. And the last problem, we're gonna use the Blaney and Criddle equation again. And it says estimate the maximum evapotranspiration of corn grown at 27 degrees north latitude over April and May. The average monthly temperatures are 70 Fahrenheit degrees and 75 Fahrenheit degrees respectively. How much water must be added if rainfall for these 2 months is 3 inches and we lose 2 inches to infiltration and initial abstraction? Okay, again, let's find the values for this. Okay, let's make this a little smaller. So K is gonna be equals to, we use 4.5, we're working again with corn, right? Yeah, corn, and we wanna use 0.85. 0.85 percentage of daytime hours per year in the study month. We're gonna use table 4.6. And for this, we gotta be a little more careful because we're given 2 months now. So let's go to 27 north. It will be between 25 and 30. So you have to linearly interpolate. And then April and May. So it will be between these 2 values and between these 2 values. So we have 2 values of P, which I have them already. So for April will be 8.654, and the way you get this value is by interpolating. And for May is 9.41. Again, this is for a 27 north latitude degrees in here. And the T, mean monthly, we're given 2 as well, which is 70. This is for April, and 75 is for May. And We got all our values. All we need to do now is plug in here and solve for it. And the way you solve when you have 2 months or more than 1 month is, let's put out equals, let's put the k over 100 on one side, k over 100, and then multiply that by pt. In our case, one of the p's is this times this, and then you add the other may. In this case, may times the may p-value times the may temperature. And of course that didn't work. Let's see what was wrong. Oh, here I missed the multiplication between those. So we go 11.14. That's about right. Let's get rid of some decimals. 11.15, and that's inches. Remember, that's given in inches. So I would say this is one of the answers, because we're asked also how much water must be added or irrigated if rainfall for these 2 months is 3 inches and we lose 2 inches to infiltration and initial abstraction. So a simple way to go with this is we are gaining 3 inches of water due to rainfall. We are losing 2 inches due to infiltration and initial abstraction. And we just solved that we are also losing 11.15 inches. I would say about 11 inches due to evapotranspiration. So we're losing 11, we're losing 2, so that's 13 inches. 11, 2, that's 13 inches, and we're gaining 3 inches. So the subtraction of that would be 10 inches. So we need to make up for those 10 inches, and that would be how much we need to irrigate, 10 inches. However, we can also use the what we get in minus what we lose out equals 0. If you remember, this is the mass balance equation. So what we're getting in, we can say, is the precipitation. Let's do in parentheses the precipitation plus the irrigation is what we're getting in, and we're losing due to initial extraction and infiltration, and we're also losing due to evapotranspiration, and all of that should be equal to 0, right? So if we want to solve for how much irrigation or how much we need to irrigate, we can do the irrigation equals, we pass everything to the other side. It will be initial evapotranspiration positive plus the initial extraction plus infiltration, all of that minus the precipitation, and if we plug our values, we get the irrigation equals the evapotranspiration that we solved up here, so it will be about 11.15 plus the initial extraction and infiltration that we say is 2 inches plus 2 minus the 3 inches of precipitation. So we get that we need to irrigate 10.15 inches. I hope this makes sense. Inches. I hope this makes sense. Technically, you don't have to do all this work. This is just to prove with the mass balance equation how much you need to irrigate. But if you are gaining 3 inches and you are losing 3 inches of water, and you're losing 10, and you're losing 13, sorry, you need to make up for those, and that will be about 10 inches. So yeah, this is how you use the Blaney and Criddle equation, the empirical formula, and again, in this part here, we also use the Blaney and Criddle equation, but for only 1 month. So I hope this video was helpful for you. Good luck solving for these problems.